Okay, so I think we are live now. So hi everyone. So after a long break of around a year, this is now the 25th edition of the InfoVisFHP talk series. And again, as last time, it's happening virtually again. And just for the background, so I'm Martin Bludau and I work at the UC Lab of the University of Applied Sciences Potsdam. And the talk series is organized by InfoVis researchers at our university, specifically by people from the UC Lab, and oftentimes takes place in combination with specific courses or course topics. And yeah, today we have Christian Tominski from the Institute for Visual and Analytic Computing from the University of Rostock. And Christian is a researcher and professor for human data interaction. And I'd say he's active in the research of data visualization, interaction, and visual analytics now for many years. And he does research on a variety of research topics as multivariate data visualizations, time series, geo-visualizations, graph visualization, or various forms of new methods for interaction, or visualization and analysis. And yeah, he recently also published a book on interactive visual data analysis together with Heidrun Schumann. And I guess he will give us some more insights regarding his research in his talk now. And so hi, Christian, and thanks for being here. And I already hand over to you now.
Yes, thank you, Mark-Jan, for inviting me. And yeah, I think we can start right away. Let me share my screen. And here we go. I'm not sure if this is today a research talk or more a series of demos. So I usually like to demo my approaches, and it will be a mix of like a bit of talk and a bit of demos and videos. And my focus today is on interaction for visual analytics, and in particular on modern interaction. But before we start, I would like to kind of set the stage by telling you that visual analytics in general is about gaining insight into data. And for starters, I brought today a small data set with three columns, ID, X, and Y. And yeah, when we look at this data, we actually cannot, when you look at this data in tabular form, we cannot really see anything in this data. So what do we usually do? We plot the data. Well, this looks interesting now, but we still cannot really get insight into the data. And then what we can do is we apply some computational analysis method. Let's do some clustering here. Okay, and we use an algorithm, and it gives us a nice series of these four clusters. But the question is this really it? Is this really what we can, what is inside the data? And the argument of visual analytics and visualization in general is that you have to have the user in the loop, so that the user can decide, look at the data from different perspectives, look at different representations of the data, and then to really get to the essence of the data. And now show you the same data, just an alternative representation. And now you see, as it develops, actually what we have done now, we have just connected the points in the data set, and we get a completely different picture. And this shows us that really it is the human who has to interpret the data and to adjust the visual representation to really find out what is inside the data. And visual analytics, of course, does not do this on just such small data sets, but usually has to deal with larger and complex data sets. And usually the data describes some complex phenomena, and the goal of visual analytics is really to gain insight into large data to understand complex phenomena. And what visual analytics, what the essence of visual analytics is, it combines computation, visualization, and interaction. And like you can think about visual analytics this way. If you can compute the answer to your problem, then go ahead and compute it and you are done. But oftentimes computation is not enough. And if you cannot compute the answer, then it's a good idea to visualize the data, to really see it and use the human capabilities in making sense of the data. But this may also not be enough. If the visual representation or a single visual representation is not sufficient, then you have to add interaction to really look at multiple perspectives of the data. And in this sense, interaction is really an essential aspect of visual analytics. Okay, and the definition from, like, say, the Visual Analytics Bible from the book from Thomas and Cook, Illuminating the Path, they define visual analytics as the science of analytical reasoning facilitated by interactive visual interfaces. So the interactive visual interface that combines the expertise of the human with the immense computing powers of the machine, and combine these things in a way that you can really make sense of data. And in this context, the interactive interface is really an important aspect. And ideally, the interaction will follow accepted concepts or paradigms of interaction, like this direct manipulation paradigm, where you say that the interaction takes place directly on the visual representation. And it's physical action that you perform, and you get constant visual feedback about what you're doing. Later on, this was expanded to a concept called fluid interaction, which then adds to direct manipulation the idea of promoting flow and keeping the user engaged in the analysis, and allow the user to really immerse into data analysis activities. So, and from this insight here, we can really see that interaction is an important aspect. So, well, but when you look at current visual analytics solutions, which focus really on the analytics parts and not so much on the interaction, then you typically see that the tools that we have, they use like standard graphical user interfaces, where you have a toolbox on the one side and you have the visualization on the other side, and you interact in one place and you see the visual feedback in another place. And so, like, it's kind of the old stuff that you're used to, using standard mouse and keyboard interaction. And the goal for today is to show you a modern approach of interaction for visual analytics. And we want to go beyond this standard interaction modalities. We want to perform the interaction exactly on the graphical representation of the data. We want to interact there where we want to really have the interaction take the effect. And we also want to consider interaction costs, so really make it, the interaction, something that is really in the flow, where you're not, interaction is nothing that distracts you, but it is an essential tool in your activity. So with this introduction, the outline for today is I want to show you modern interaction for visual analytics structured in 3 parts. We will look at 3 different types of interaction, so to say. One is the exploration of data. Second is the adjustment of data. And third is the comparison of data, where when I say data, I actually mean the data and, of course, the visual representation of the data. And these are, for each of these 3 points, I have 2 examples. And yeah, I try to show much of the content via demos. Okay, let's start. The first thing is we want to talk about today is exploration. And the example that I've chosen here is a hierarchical graph. A hierarchical graph is a multi-scale graph representation, where you can expand a node to get to more detail, and you can collapse a subgraph to abstract the graph. And this will actually be the first part where I would like to show you how this works, and I will share another screen. Okay, I hope you can see this. This is a graph visualization tool that has many different windows, but let's focus on the central part here to just see how this hierarchical graph works. You can, like you have the graph, and then you can expand the nodes, and then you can go to the details and decide where you want to go, and then drill down into the details of this graph. And when you go the opposite direction, you collapse a subgraph to get to the next higher level. Okay, and the question now is, let me switch back to the presentation. The question now is, how can this exploration be supported in modern visual analytics environments? And I've picked two examples here. We want to explore the hierarchical graph on a high resolution display wall, and we want to explore it on a tabletop surface. And when we imagine ourselves standing in front of a large high resolution wall, and we have the hierarchical graph visualized on that wall, it's obvious that mouse interaction will not be sufficient here. And instead, what we want to do is we want to utilize the space in front of the display for the interaction. And in particular, we want to control the level of detail or level of abstraction, however you want to call it, by moving toward the wall or away from the wall. And the principle behind this is called proxemic interaction. This kind of interaction works is based on spatial relationships between objects, where spatial relationship can mean proximity or orientation. And concretely in our example, what we do, we track the human moving in front of the wall, we track the user's position, and we track the head orientation. And what we further do, we subdivide the interaction space into zones with increasing distance from the wall. And this is illustrated here. Now, as you can see, we have the wall in the background, and then we have, like in this example here, 3 zones. And when the user moves forwards toward the wall, you will get the higher details, so the nodes will be expanded. And when the user moves away from the wall, then the nodes will be abstracted, and you get a higher level of abstraction. And when you have these zones, you will have this effect being applied globally for the whole graph. So like you have a level-based access to the different levels of abstraction. But you can also add the head orientation to this model of the zones. And based on the head orientation, you can project a window onto the display wall, which corresponds to the location where the user is looking at. And then you can control the level of detail exactly in that window. So when I look into this area and step forward, I will only get details in this part. And then when I look into a different part, I will get the details there. And when I move back and forth, I will see the different levels of abstraction. So this is one way how physical navigation can support the exploration of a hierarchical graph on a display wall. Now let's switch to here are like screenshots of or photographs of this scenario with these funny tracking markers to get the head orientation into position. And this is the overall setup. And the ellipses here in the center is the part where the user is looking at. Okay, but now let's switch to the next example, and which is tangible views above a tabletop display. Here in this case, the hierarchical graph is visualized on the tabletop display plus tangible views. Well, what is a tangible view? A tangible view is a display, and at the same time, it's an interaction device. And this is the interesting thing about tangible views. A tangible view is something that you can hold in your hands, and in particular, you can hold it above or in the space above of a tabletop. and display. And the level of detail for our hierarchical graph can be controlled by lifting and lowering the tangible view. So the principle here is, or the interaction paradigm is called tangible interaction, where the focus is on the manipulation of tangible objects. And in our scenario, what we do concretely, our tangible view is nothing else than a simple cardboard onto which a visualization is projected. And this cardboard is, has some markers, and the markers then can be tracked in space, so we know where this cardboard is in the space above the tabletop display, and we also know the orientation of this piece of cardboard. And with these things, with the spatial awareness, we can define a whole interaction vocabulary. And this is illustrated here. So you can move, so like the gray part is the tabletop display, and the brown things are the tangible views. And then you see what you can do with for the interaction. You can move the tangible view up and down. You can move it horizontally above the tabletop. You can rotate it in different directions. Then you can detect gestures like tilting the tangible view or shaking it. You can freeze directions of movements, which makes the tangible view insensitive to a certain direction of movement. You can use different shapes or colors of cardboard to like have a whole toolbox of things, what you can do. Or you can, for instance, you can also flip or wipe above this tangible views. So here's the example where you have in the background the original graph, and then you have a tangible view, and by lifting and lowering it, you can access the different levels of detail. There's a YouTube video that you probably, yeah, it would be good to copy this into the chat actually. Okay, but I wanted to show you, when you follow this video, you will find that this concept of tangible views does not only apply to hierarchical graphs, but you can do all kinds of visualizations, interaction for all kinds of visualizations. Here's an example where you have a parallel coordinates plot, and you can like lift and lower the tangible view to access different levels of abstractions for these parallel coordinate plots. Here's an example where you have a map-based visualization, and you can flip this tangible view to switch to a different color coding. Okay, and I encourage you to really follow this link and see how this works in action. Okay, so now these were was for the exploration part. So we have seen how like novel interaction modalities can be utilized for exploration in the context of visual analytics. For the second part of the talk, I would like to switch to adjustment. Right? What do I mean by adjusting things? The first thing is what I initially said. Usually you need to have different visual encodings and different layouts of the data to facilitate different tasks. And I would like to illustrate this with an example. Here we see a spiral visualization. This is temperature data. And this is aligned along a spiral, like it's about 3.5 years of data, daily temperature data. And the visual encoding is one that supports identification tasks. Identification tasks are tasks where the goal is to really identify a specific, or identify the values that we see. And in contrast to that, I show you another visualization, which is exactly the same data, but a different visual encoding. And this encoding is good for location tasks. Location tasks means we are interested to see where in the data, in our case, where in time are specific values located. And what we see in this visualization, the extremely cold and the extremely hot days, I use a special color. And this allows us to really easily locate where these values occur in time. And we see by this example how important the visual encoding is for the task. So in other words, we need methods and interaction techniques that allow us to change the visual encoding and also the layout in the sense that we adjust the visual representation interactively. And later on, I will show you an example with a modern interaction approach, which is interactive lenses. The other part where adjustment is important or can be important is when you want to adjust the data. So data is usually not free of errors, so it can be necessary to really correct wrong data or add missing values by adjusting the underlying data. Another thing is that you, by adjusting the data, you can really play with what-if scenarios. You can edit a data value and see how this, or a series of data values, and can really see how this edit operation affects the overall properties of the data. So I have these two things, adjustment of the visual representation and adjustment of the data. And for this second part, I will show you responsive matrix cells as an example. Now let's switch to the interactive lenses. Several years ago, so the original idea of magic lenses dates back to, I think, 96 or 94, under the term magic lenses or looking glass tools. And several years ago, we wrote a survey on interactive lenses for visualization. And the definition in this context is that an interactive lens is a lightweight, is important tool to solve a localized, is also important, visualization problem by temporarily altering a selected part of the visual representation. So we have something that is lightweight, it is easily reversible, it is localized, it works on a selected part of the data only, and it is really a temporary thing. It's not that you apply a change and then this is permanent. No, you have something that can be easily switched on and off. And this is a basic schematic representation of this idea. You have a base visualization, in this case, a simple bar chart. And within the lens, you show an alternative representation. And in this case, it's just illustrated by different colors of the bars. And the lens can have different properties, orientation, shape, and size. And the most important property is the position. This is where the high degree of interactivity of lenses comes from. You can easily grab a lens and move it across the visualization to adjust where you want to see the lens take effect. And lenses can be, so in our survey we have more than 50 lenses collected, and here are just 3 examples. A lens can alter the representation. In this case, a time series is altered based on some alternative computations. Here, the sampling lens just samples lines in a parallel coordinate plot to deal with clutter. And this eccentric labeling lens, which is a lens that adds labels to the data points within the lens. Okay, and the particular example that I want to show you is again related to graph visualization. And for this, I would like to switch again and show you a demo. Let's see if this works. Here we go. Okay, I hope you can see this. What we have here is a graph visualization. Oh, the lens is already activated, just deactivated for a second. And yeah, it's in a zoom space, and you can zoom, and you have a layout computed, and you want to zoom and like look at the things in detail. Okay, this is a kind of made up scenario. Usually you have a larger data set with much more data and information, but for the demo it should be fine. And now one particular thing that you can have is like a situation like here for this node. This node has some neighbors, and then there's also some edges going about this node, but we cannot really be sure if these edges really connect this node or if they are just going to another node. And one lens that helps us clear the situation is the so-called local edge lens. And this lens cuts off all the edges that do not connect to the nodes within the lens. And with the help of this lens, we can really see that these three lines that are just passing by this node and not really connecting to it. Now with this lens, we can clear edge clutter. Okay, so this is nice. And we can now really see that, okay, we have 1, 2, 3, 4, 5, some numbers of edges. But what we cannot see the actual neighbors of this node. So what we would need to do is now zoom out, look at where these edges connect to nodes, and this would need some additional steps of interaction. But instead of doing that, I apply another lens effect, which is called the bring neighbors effect. And this effect, and this is now back to the idea of adjusting the layout of a visualization. In this case, when we move the lens towards a node, it gradually attracts the neighbors of that node. And when I'm really on the top of the node here in the center, I have all its neighbors within the perimeter of the lens. And this way, I can create a local neighborhood overview by adjusting the layout and using the lens, like this way. And I do not have to do some global zoom and pan operations. I can just use my lens in the local view. Okay. And now, if I know how the neighborhood looks like, I can then decide if I want to go somewhere. Like, I'm not sure if we have implemented this. No, not yet. Okay, but anyway, this is for the lens demo. And if I do not need the lens anymore, I just switch it off and I'm done. Okay. Then let's switch back to the presentation. Yeah, and then you can, of course, also go to this URL and play with the tool for yourself. Now, this was about the adjustment of the visual representation, and now I want to go on with adjusting the actual data. And what we now do is we expand the idea of the graph to something that we call a multivariate graph. And the multivariate graph is that has a structure and also has attributes associated with the nodes and the edges. So, and we visualize this multivariate graph as a matrix, but this is not a regular matrix, it's a specific matrix with two different visual encodings. In the lower triangular part of this matrix, we visualize the graph as we might be used to, like two nodes are connected. When two nodes are connected via an edge, in this part, the cell is marked, and the color of the cell also shows us the weight of the edge. If there's no mark, then there's no edge between the two nodes. This visualizes the structure of the graph. And in order to also visualize the attributes, we use the upper triangular matrix to show the pairwise similarity of nodes, where the similarity is computed based on the attributes, which means that the color of a cell tells us how similar are two nodes based on their data attributes. In a sense, this gives us an aggregate value of the attributes of two nodes, of two objects. So, but because this is an aggregate value, we do not really have access to the underlying attribute values themselves. So the question is, how do we get access to these attribute values? And then how can we edit them directly in the visual representation? And the idea of responsive matrix cells is to use a focus plus context resizing of the cells, and then embed dedicated views into these matrix cells. And these matrix cells are then responsive to size changes. And when there is enough space, so we have enlarged a cell far enough, then edit interaction is possible. And then we can edit. So this is a screenshot. I show you in a minute just a quick demo of this. And within these views, we can now directly grab the graphical marks in this representation to edit certain values. And while we do this, the underlying visualization is really updated on the fly. Let's see if we can show this as a demo as well. Stop share here and share another screen. And here we go. This is the matrix that I showed you earlier. And now I show you how you can embed a view into this matrix. You just drag a part here, and then the cells get automatically expanded. You have a global zoom, but you can also like have a local enlargement of this. And then within this part, you see the underlying data values being visualized. Different representations are possible. Here is a bar chart, and a bar chart with different orientation. You can have a parallel coordinates plot, or you can have a star plot. Maybe just add another attribute to this plot. Let's see, accurate passes. Okay. And now when you zoom out and you zoom in, you see that there's more details coming in, like the labels and so on. And then when you are large enough, you can really grab the control points here and really edit the data. And what you just saw is that this bar, this column here, changed its color because this edit has affected the similarity of this node. And in this way, you can like manipulate the data and set up certain scenarios. For what we see here is soccer data. So people with their, so players with their attributes and the teams they played in together. And so like this tool could be helpful. So this manipulation of the data could be helpful for example, for planning the next season, to see which players I would need or what properties my players would need in the next season to be like similar to another team and maybe beat it. Okay, and you can have like several of these cells in the same matrix and different representations. And maybe one thing that I also wanted to show is this is a star plot that shows all attributes of all like involved nodes. What you can also have is unit cells where you have this pairwise display in a pairwise fashion, so that you have only the, for each of these smaller views, you have just the two nodes that are participating in one cell. And here you can see like the responsiveness also of these cells. When I zoom out, the representation gets more abstract, and as I zoom in, you can see more details and then edit the data. Okay, this was it for this demo. And stop sharing that and go back to the presentation. Okay, so with this, we finished the second part, the adjustment. And now for the final part, I would like to talk about comparison. And comparison is really one of the most important tasks that we have in visual analytics, because much of the sense making involves comparing things, like is A greater than B? Often it's not that simple, like but this A greater than B is kind of a precursor to all kinds of other more complex tasks. Like in order to identify a trend, I need to make comparison of the individual data values in that trend. And then you can also have higher level comparison. I may say, is one trend steeper than the other? So this is not just comparing two values, but comparing two more complex objects. Okay, so comparison is really important. And the general procedure of comparison is that you first have to select what you want to compare. And second, you carry out the actual visual comparison. And then as a third step, you usually need to understand the data and the comparison in context, so that you are no longer limited to isolated values, but you need to understand where these values are located and what is related to that. So you have these three steps: select things, carry out the comparison, and understand the data context. And then again, I want to show you two examples. The one is naturally inspired interaction techniques for visual comparison, and the other where I want to add the notion of interaction costs to interaction techniques for visual comparison. So let's start with the first example, and this was the naturally inspired visual comparison. This research started from the question of how do people actually compare information in the real world? What do they do when they do comparisons? And well, when you think about it or like observe people, then you will see that they do one of these three things. They arrange the information side by side so that they can compare that. Or they stack the information, like in this case, it's bar charts printed on paper. And then the stacked papers are held against the light to let the information from one sheet of paper shine through the other so that you can make the comparison. Or you just fold, so you stack again, but for the comparison, you just fold the occluding paper back and forth to make the comparison. And what we did is we replicated these interactions as interaction techniques for visual comparison. And the starting point is that you have a visualization, and what you can do, like let's say you have a matrix view, which is called the main view, and then you can extract arbitrary subviews from this matrix. So in a sense, this is something that you cannot do in the real world, but you can do it on a computer. You just mark something, and from there a subview is extracted and now exists as a self-contained visualization view within this virtual visualization world. And well, these subviews can then be arranged and manipulated for the actual comparison. And this then can be done according to these three things that I just showed you. You can like grab a view and arrange them side by side, and then can make the comparison. Or you can stack the two views above each other and then use alpha blending to let the information shine through, which is illustrated here. Like the top view, the view called B, is now gradually faded out, and so the information of the underlying A gets visible. Or you can do this folding interaction to uncover the information that is below this view. Here is a link to a YouTube video, but I can show you also a live demo. And let's see where we have this. Here we go. So again, we have a zoomable space. There are some like test visualizations. There's a matrix, there's node link representation, and a table lens visualization. And here's something that is called a node-trix visualization, which is a hybrid matrix and node link visualization. And what you can do here, you can go to a certain part here and then create a, oops, create a subview, which I do now, and then you have it separated and can move it around as you want. And what you also see, there's this red frame appearing, which shows you where you have extracted that view. Now you navigate further, and then you think, oh, this looks interesting. Oh, well, I want to compare that to this other view that I just extracted. And in this case, we can use a shortcut. The bring shortcut, which just brings me this view into the current viewport, and then I can arrange them. Now make them a bit more transparent, align them, and then I can like compare how these things look like, either with the shine through or like with this folding technique. Log back and forth and see how things compare. So the question is, it's not easy to decide which technique to use. For instance, in this node link representation, using fading is kind of difficult because you cannot really follow what lines change and so on. And here I would say like it would be interesting to use the folding approach. And the unfortunate thing about the folding is that you have this collateral occlusion from the fold. And then again, you can use different folding styles. Let me see. Like you can just use a blank thing, or you can just use a shadow, or even just indicate where you fold. Well, then it works more like blinds than a fold. Okay, and also a particular thing regarding the folding interaction. Certainly you have seen this in other tools that you can grab an edge and peel it off to do the fold. For this particular implementation here, it's not useful to really force the user to move the mouse to the edge of a view and grab it and unfold it. Instead, you can really trigger the fold where your focus is. Like if I'm interested in this node and want to see what's behind it in the other view, I just click it, and the fold is computed automatically based on a heuristic, uses the smallest distance to one of the corners, and then initiates the fold with a force-based animation. So the user can like stay focused and does not need to move the mouse away from the focus in order to perform the interaction. Okay. Now, just move on to the last and final example, and this brings us to the consideration of interaction costs. So of course, all these things involve some costs. Regarding the procedure of the comparison. And the first step was to compile the set of objects to be compared. So we have costs for selecting these objects. The second step was to carry out the visual comparison. So we have the cost for moving our eyes back and forth between the objects to really draw the conclusion about the comparison. And finally, in order to understand things in detail and in context, we have to navigate. And so you have the costs for navigating between the objects of interest. And one particular example here is a map. And now consider you have to compare like this dark green area here. Is it darker than this dark green area here, or darker than this one or this one? So like this conclusion is really difficult to make. And why is it difficult and costly? Because there are distances between these objects, right? And the comparison would be much easier when you can reduce these distances. But how would you want to do this on a map where the areas have a fixed location? Well, this is something that we can solve with the help of the comparing. A technique that is based on 3 ideas to keep the costs in check. First is the semi-automatic selection of comparison candidates. Then we have a dynamic rearrangement of data objects to be compared. And then there are navigation shortcuts that just allows to navigate between the objects effortlessly. And the idea here is, and I show you a demo soon, that once you have a selection of objects you want to compare, you activate the ring, and the areas are dynamically relocated to this ring. And in this sense, you have them all side by side, and they are now much easier to compare. So since we have relocated these areas from their original position, it is good to provide an indicator of where these areas have come from. And this is the purpose of this indicator arc. The arc shows in the direction where this relocated area originally came from, and the width of the arc tells the user how far away is this area located in the original way. What this indicator arc has additionally is a color coding. And this is a local color coding. Based on what my focus is, where my mouse cursor is hovering, the area where my mouse cursor is in the focus. And based on that, local differences between the values of these areas are computed. And then a blue arc shows there's the value of this area is below the focus area, and red indicates it's a higher value. Okay, enough for the talking. Let's look at a demo. Share screen. And here we go. Okay, this is our map. We already have activated the ring. Let's switch it off again. So maybe first, the idea of the semi-automatic selection. I click an area, and then automatically the most similar objects are selected in this basic demo. Of course, you can use more complex criteria to automatically select comparison candidates. And now when you have your candidate selected, you activate the ring, and the areas are brought to this ring, and now you can compare them in detail. So now imagine you have a far bigger map, and then you are zoomed into this map. You can use this ring to navigate between the objects you compare. And you see how the indicator arcs adjust themselves to indicate really the direction where these areas are located. So another thing is, so I said the automatic selection selects areas that are, those values are most similar. So from looking at this green color coding, I would actually not be able to really identify any difference between this, between the underlying values. All are dark green. But this color coding is a global one between the global minimum and maximum. Now, the indicator arcs that we use, they have a local color coding that only considers the 4 selected areas. And this makes small differences visible. Like when I focus on this part, I can see that the left 2 areas in the ring have a lower value indicated by blue arcs, while the directly to the left area has the highest difference in the negative direction. And the right areas, they kind of have this pink tone, so it's toward the red, so they have slightly, but only slightly higher values than the area that I'm currently hovering with my mouse cursor. And so I can make the local comparison, and I see how the indicator arcs change their color when I focus on a different area. And in this way, I can really facilitate the comparison. And in order to, like, if I want to understand now the thing in context, I can do like a kind of data-driven navigation. I look here, I find, oh, there's something interesting in the surrounding of this area, like this one here. I select this one. Automatically, I get the most similar ones there, and then I can navigate again. oh, I find something interesting, oh, over here, select this one. The most similar ones will be brought to the comparing, and so on. So I really have a nice comparison tool where the user really stays in the flow and is not distracted by other operations, or even has to resort to a graphical user interface in the standard sense. Okay. So in summary, so the core idea of this comparing is that the user does not need to collect the relevant information him or herself, but instead the system brings the relevant information to the user. So, and with that, we've covered all the three topics I wanted to talk to you about today. And I hope that you take away three messages. Interaction is a key component of visual analytics. You have seen the 6 examples of modern interaction, and maybe you find some of these useful or inspiring for your own work. And personally, I think that this kind of flexible information access is really, really important so that you can really get the information where and when it is needed. And what would be interesting topics for future work? We have seen like interaction modalities or interaction techniques that are always designed for a particular thing, for a particular view, or for a particular device. And it would be really interesting to have interaction techniques that work across views and across devices, so that you can implement interaction once and reuse it for different modalities or different views. This also brings us to the topic of conflict-free integration of interaction modalities. So this is something that is not easy to do, like really, and to have multimodal interaction. That is something that is interesting to research in the future. We just basically briefly touched upon the aspect of costs of the interaction. This is something that deserves more attention in the research. And of course, most of the examples that I showed you are really handcrafted examples, and there's usually no toolkit support for these kinds of interactions, but it would be really helpful and would make other people's really easier if there was toolkit support for modern interaction. And with this, I would like to thank you and also point you to this book. Many of the techniques I talked about today are also described in this book. And yeah, if you have any questions, yeah, I'm happy to answer them.
Thanks, Christian. There are actually already some questions, but I will start with my own. We at the UC Lab, we usually work a lot with applied research projects, like we have specific collaboration partners that give us their data, and we try to work on solutions mainly for this specific data set. How does it work, like with, or how did it work with these projects that you showed us? Was it like also for specific data, or how do research projects at a university look like?
Yeah, yeah, I completely understand this question. I personally like to think, so if I stumble upon a problem when I'm exploring a data set, I try to solve it. And this is sometimes my inspiration to really, oh, I would like to do this, but I cannot do it with standard approaches. So I sit down as an engineer and implement something that helps me solve this problem easier. Then you have other sources of inspiration for this naturally inspired interaction technique, for instance. I remember a flight back from a VIS conference where someone in front of my seat was doing exactly this, folding back and forth a report. And I said, well, this would be something that would be interesting to do on a computer and use it for visualization. And then you have really also applied research questions. I've not showed you this example, but several years ago, we also implemented something that is called the edit lens. which is a lens that allows you to insert new data into a graph. So like the scenario was the following. There were people from the biomedicine, and they have a network of brain connectivity in rats. And each time a new publication comes out, they identify new connections within the brain, and they have to insert an edge into their data. But the already existing network already serves as a kind of map for these people. So you cannot just change the overall layout of this graph as soon as you get a new edge. But this would usually happen when you apply an automated algorithm. So with this edge lens that we implemented, we really gave them a tool to have a cost-efficient way to insert and locally route new edges and new nodes into their network without disturbing the other parts. So to summarize, there are these things that come from your own inspiration or your own problem that you have. Then you have inspiration from the outside, and you have these applied things where you really have someone else having a problem and you want to try to solve it.
Okay, thanks. And then we have a question. First of all, thank you for the talk. The interaction and all demos look incredibly smooth. And the question is, are they all web-based, or what is the magic behind it?
Yeah, thanks. Well, yeah, it kind of looks like magic, but I think careful implementation is the key here. So my early demos were implemented using OpenGL and Java. And with OpenGL, you usually have enough graphics power that you can get the smoothness. And recently I've moved to web-based demos, and there I use just the canvas rendering. Of course, you could be faster when you use WebGL. But instead, what I did, I just reduce the data size to have the nice demos. But this is just an implementation detail. And I also want to add that getting this interaction really to this degree of smoothness that you saw in the demos, it really takes a lot of effort in the implementation. And I totally agree that oftentimes you cannot afford spending that much time on polishing the interaction. As interaction is my favorite topic, and I'm at the university, and this is my core research interest, for these examples that I show you, I took the time and really tried to make these smooth, because this is my argument I make. Like, interaction is important, so it should really work smooth and nicely. Maybe you can compare it with computer games. You can have the nicest graphics, but when the interaction or the combat system is crappy, it's not worth it makes no sense. So you really have to spend some time on interaction. The only question is how much time you can afford polishing this.
Okay, then there is a question by Marian. Some of the interactions look quite advanced in their handling. How do you ensure that the interactions can be discovered?
Yes, this is an interesting question. Yeah, usually what you may have seen in one of the demos is that at the side there's kind of a help bar. In this recent demo of the responsive matrix cells, maybe I return to that for a second. I hope you can see this now. Yeah, there's this menu here, and there's a help button right at the top, which brings you down to this explanation. So it is complicated at times, especially when you have these advanced interactions where you have many things that you can do. And I would argue, give the user explanation or a tutorial. Again, I refer to computer games where you have a kind of tutorial that you can make. This is something that we would really need. I think this is now something that's called onboarding or something like that, where you really try to get the users into your system. On the other hand, there's also the argument that you do not really, so you want to interface to be invisible. Everything comes naturally. I think this is a challenge, especially regarding the discovery of things. Yeah, but then again, it's a question of how people are trained and used to using these kinds of techniques. For instance, when I switched from a regular phone to a smartphone, I really had difficult times understanding that scrolling beyond the top is kind of a reload thing, right? And I was not used to it, but now I'm used to it. I'm no longer questioning this, and it's nothing that is documented anywhere. You just discover it by accident or by someone else telling you. And yeah, so I agree. It is important to really like have mechanisms in place that make interactions discoverable, but at the same time, when you know what you're doing, these mechanisms should not stand in your way and distract you from your work.
So would you also say that it depends on the targeted users, like if it's like an expert tool or something?
Yeah, definitely. So it's the same thing like for standard user, the person might be happy really with a graphical user interface, and as soon as you become expert, you just want to have shortcuts and do things like really quickly, and really depends on the user you are targeting.
Okay, and now for now, there's one last question by Rosa. Thank you for the talk. Really great to see the demos. Regarding the naturally inspired visual comparison approaches, have they been tested with users?
Yeah, when you look up the paper, there is a study. We conducted a small qualitative study, but the study was not to compare which technique is best for certain tasks, but we only studied how well the interactions themselves are perceived. And I totally agree that a quantitative study telling me, yeah, this technique is suited best would be really nice to have. But then I would also say it is not easy to arrive at such an absolute answer, because it really depends on the visualization that you have at hand. For some visualizations, these shine-through things work absolutely well, but as soon as color is involved, this shine-through is no longer that good, because you get merged colors, which might not be in the color scale that you have for the visualization. Another problem is all these things that resolve. So first of all, when you arrange things side by side, you do not have occlusion at all, but you have the difficulty to really reference one thing here with the other thing there. So this is costly, of course. So that's looking back and forth between the two. You can avoid this by really co-locating the things exactly on top of each other. Then you have the problem of the occlusion. And then it's the question how you resolve it. So there are quite complicated things going on. And so I think our paper ends with the statement that we make our software available to anybody who wants to test this. But actually nobody asked. Maybe this is an indicator that it's really not easy to really design experiments that give you the answer of what of these techniques is really the best. And I'm not sure if there is a best thing at all. Maybe they are all good, and it's all good that you have them in the toolbox and let the user decide what he or she wants to use.
Okay, thanks for the questions and also the answers. I think I will look around if there are any more questions somewhere. I think there are no more questions. So I would say, well, I would say thank you, Christian, for the talk. And yeah. Maybe, yeah, someone asked in the beginning about links for the demos. I think they were all in the slides, right?
Yeah, I think, yeah, maybe I just sent them to you, and then you just add them to the YouTube text.
Yeah, I will do this.
Yeah, and then you have all the links and do not need to write them down manually from the stream. And you can also, yeah, I invite you to really play with the demos. There are more demos on my webpage on other softwares, and I also like, if you're interested to read about this, then look at the book. And yeah, it was really exciting to have the talk today.
Okay, thanks, and thanks for watching, and well, see you for the next talk, which will actually happen in 2 weeks, I think. So ciao, everyone.